Okay, welcome back, everyone. Although there are not that many people in the lecture right now, unfortunately. So I'd like to start with a postmortem of the midterm. Does anyone have any comments about the midterm?
I'm gonna say one thing.
Mhm.
The bonus is difficult, and there are a lot of things to do, and I mean it doesn't. It sort of feels like 75% of all homework combined, but to complete that within like 2 days, it feels like more than the total amount. That
Yes. Oh, did you want to say anything else? Or
that's what I'm gonna say here. Yeah.
right. Anyone else? So I suppose then, as a preface, what's the midterm? The midterm was, in some sense, a gauge of preparedness. And in some sense, it was a device that was useful for me in order to get people to catch up. And several people came through. Several people, even who I spoke with, actually gave up and didn't submit, which was very unfortunate. And it wasn't an outcome that I wanted. And the results were really mixed. So don't worry about your performance. Now, what I'm trying to teach you, and this is something that's very, very difficult to learn, is general abstract reasoning skills that are useful, incredibly useful in almost anything that you can possibly do in life. And those skills are very hard to acquire. And acquiring them is very frustrating. But it's very important that you do so. So there is good purpose to be gained by going through this. And naturally, going through the process of acquiring them is very stressful. Now, the difficulty of the midterm was such that precisely the strongest students in the class were just barely able to finish the exam, 2 students, in the allotted time. It was exactly at the maximum difficulty that they could have reached in that time frame. And now, if you want me to go through a rundown of the results, I haven't graded the proof problems yet, but this might just give you some perspective. So there are 19 people enrolled in the class, and 15 people submitted work. 4 people did not submit. So if you did submit work, thank you for doing that. Thank you for putting in the time to work on the midterm. Uh, Hopefully the objectives and the goals of actually giving you an idea of, well, here's some notion of abstraction. This is how we think of things in abstract terms. And then eventually it's a skill that you really have to work on for a very long time. And it's very unfortunate that this class is a 5-week course, because it's almost an impossible task to set to teach people abstract reasoning skills from the ground up in 5 weeks. That's very difficult. And so thank you for working within those circumstances. Okay, so now the results. I'll mention the programming problems. So PG1, I'll just list them here. Let's see. Yep. So there were 4 programming problems on the non-bonus sections of the exam, and then there were also bonus problems. So here's the number of people. Let me switch here. That got correct answers for each one of these problems. So of 15 people, PG1 was the sublists problem. 8 people had correct submissions. For problem 2, 6 people had correct submissions. For problem 3, which was to write the sublist problem using foldr, 7 people had correct submissions. And for the fourth programming problem, which was the proof problem, no, this was not the proof problem. This was the higher order functions problem. And we'll talk about this one. Three people had correct submissions with 2 partial. And then for the bonus problems, well, 2 people went for the bonus problems, and both of them solved Q12. So 2. And then what happened was that if you actually looked at Q12, it asked you to implement perms using just lambda and some functions. And then the other 2 bonus problems allowed you to use foldr and unfoldr. So the restrictions on Q12 were stricter than the other 2 problems. And so 2 people were able to solve the bonus problem. But that was really, really a tricky problem. The solution is a terrible, frightening mess of parentheses, as some can attest to, right? And then, okay, well, then let's look at the proof problems. So I looked at PF5. That's the only one of which I'll speak. And this was about racket if. So for this problem, 9 people submitted, and 3 of the responses were correct. And the people getting correct responses to these problems were mostly the same people. So if you look at this, of what was not necessarily the simplest, but probably the most approachable programming problem on the midterm, of the 19 people that were enrolled, 8 submitted correct solutions. That's less than half the class. So that's not an ideal outcome for me. And there might have been issues about calibration of the difficulty of the midterm, or maybe how I could have made it more approachable. So I didn't necessarily succeed in doing that, especially for the 4 people that didn't submit work. I consider that a failure on my part. But the maximum level of difficulty on the midterm, that was calibrated exactly so that the 2 top performing students in the class just barely got through that. That was very hard for them as well. What do people think upon seeing these numbers?
I have a quick question.
Mm-hmm.
So for the 2 people who submitted their answers for the bonus, did they submit answers to all 3 of the questions, or?
Oh, well, they submitted, okay, one person submitted all 3. The other submitted only 2 of them, because he didn't realize that he could have submitted his problem as solution to the 3rd one for the previous problem successfully.
Ah.
Okay. That being said, the second bonus problem, I never actually implemented a solution that used unfoldr purely with no use of the Y Combinator. I had a solution in mind. It was fairly elaborate. Annotate each of the items in the list with a label from 1 to n, and then generate a sort of cycle which would permute elements, and this would go through all of the permutations, and in each state you depict it. That is a very elaborate and complicated solution that's very difficult to implement, and I didn't implement it myself. So the easiest way to solve that problem would have been to solve Q12 and use your Q12 submission.
Okay.
which is something that I was aware of when I set the problem. Now, Q12, yes, I threw in this Y Combinator trick, and it was basically, here's a new trick with almost no explanation, figure out how to use it. And again, that was that was a bonus problem in full earnestness of the word bonus. Does anyone else have any thoughts about these numbers?
Have you just like not looked at the other proofs yet?
I haven't graded them. I've looked at a very small number of submissions, but I can't say something intelligent about the general performance on them yet. But seeing which solutions on PF5 were correct was almost instant. So again, only 3 people got this. The answer is no, that my if and if are not equivalent. So my if is defined as follows. So let's say R, S, and T. And then there's a con statement. And then if R, then you do S, else you do T. So the key difference is that this is a function. This is a procedure definition. This is a function. So as a result, when you make a function call, before calling the function, both arguments get evaluated. So if you say, for example, my if, then let's say true. And then let's say here your argument is a fine one, and here your argument is something like first of the empty list. So this call first to the empty list will produce an error when this gets evaluated. Evaluating this produces an error. And when you call it as a function, before the function gets called, it evaluates both arguments, all 3 arguments. On the other hand, if this were just an if statement, it would look at the condition, it would see it was true, and it would never take the false branch. So the order of evaluation is actually detectable in this way, the difference between the order of evaluation for functions and if. And then another type of solution, if you didn't want to use errors, you could have also written a function call that causes an infinite loop. That's sort of a more pure solution because errors are some slightly more sophisticated mechanism, but even with just lambdas, you can do it. Any other questions?
So this is a counterexample, or?
Yes. So if you do, this was, so running this line will produce an error. So this produces an error. I'll write it in red. Whereas running the equivalent with true produces 0.
Does this have to do with the types, because 0 is a number and the other one gives back the first of an empty list, which is not a number?
Well, the first of the empty list causes an error, so you could have put any computation there that causes an error. You could have also put something that actually is a non-terminating computation that theoretically produces a number. And so in some subtle way, you can say that this actually does not have things to do with types. So for example, you can write perhaps a recursive function that whose signature is number to number, but it just keeps calling itself on other numbers and it never terminates. And sometimes you can type that still as a function that returns a number despite the fact that it's a non-terminating computation.
And this is before it never reaches the conj. Is that what you're saying? Is this at the time it's evaluating the arguments?
Yes. If substitution into the cond actually happens, then the behavior is the same. But before substitution into the cond happens, for what RS and T are, bracket will first evaluate what RS and T are. And in some way, when I modified the exam to give a hint about the first problem that said, well, okay, I've just thrown a bunch of congruence, a wall of congruence rules at you. The real effect of those congruence rules were that you could have ignored them and then peppered your justifications with a bunch of congruence before it, rules, invocations before them. And I said that you shouldn't think of them for that problem as affecting the order of computation. And then I made a remark about the order of computation in brackets, about how a function will evaluate its arguments from left to right before actually performing the body of the function. And that was, in some sense, a hint towards this problem. Sneakily put in there. Again, a lot of this was me throwing in subtle tricks. Just because the information was there doesn't mean that I made it easy to find or expected you to find it.
So for MTPG4, was it like 3 fully correct solutions and 2 partially correct solutions, or is it 1 fully correct and 2 partially correct?
3 correct solutions, and then 2 people got 10 points. They actually, I think one of those people didn't do point free, so I think one of them was an 8. And then 2 people got the point free problems. But the 2 partial solutions, okay, maybe, so 5 people solved some number of the earlier parts.
Got it, thanks.
There were not only 5 people who got any points on it. By partial, I meant they solved the first 4 parts at least. So maybe it's actually 2 and 3 partial. No, 3 people got, okay, I'm not sure if I counted these as 10 points or 15 points, but 2 people got 15 points. Let's say 2 and then 3 partial. No, I think in earnest, 3 people got 15 points. Okay, never mind. So yes, this problem was, you had to really abstractly work with the functions and abstractly think about composition. And you have to put your mind in that frame of reference where you're abstractly playing with things and twiddling them around on the page, and almost in your mind keeping them as tactile objects that you can compose in reverse. So it takes a while to train yourself to think like that. But I can give you the examples of how you'd implement the earlier functions for PG4. So the earlier functions for PG4. So let's say, for example, currying. So currying takes a function that takes multiple arguments, and it makes it possible to plug in those arguments to the function one by one. So for example, if you curry multiplication, then if you evaluate this curried function, which is now a function that only takes a single argument on 5, then what you get is something equivalent to approximately lambda x, or in bracket language. And then the body of the function in which the first argument has already been set to 5. So currying multiplication and then passing it 5 returns a function that multiplies its argument by 5. And so then how is currying implemented? Anyone?
I think what I did is I had like 3 nested lambdas. And so if I had like lambda x, lambda y, lambda z, and then at the bottom, I think I had x, y, z in parentheses, something like that.
What is the purpose of, so f is a function that takes 2 parameters. Oh, let's write down the signature as well. Let's actually do the signature before that. So let's say comments, curry. So I have called these alternatively signatures or contracts. So currying takes, what does it take? What is the type of its argument?
Function?
Of what type of what?
Two variables?
Yes. So we're going to use type variables for those. And then it outputs something. So that's the inputs to currying. And then what's the output?
Function of one input?
Yes. And what does it return?
Another function of one input?
Yep. So by the way, in the way that we write them in logic, all of the 2 sets of parentheses here don't actually have to be written. In logic, we assume that implication is right associative. So these brackets would be inserted in the way that they are without us having to write them. But here it's explicit that's, okay, this to this. Right, so going back to how you implemented it, you have 2 lambdas, lambda x, lambda y, right? So you've taken a function, now you're returning a to b to c, right? So the body of the function is supposed to be an implementation of some term of type a to b to c, right? So what did you say you do?
Well, I had 3 lambdas, x, y, and z.
So, but then a lambda is always a function type, right?
Sure.
So here you have a function that takes something. Oh, I see what you did. You implemented curry not as a function, but you just defined curry. So you wrote it in, well, it's not in point free form because you have lambdas, but I see what you, so see how this is a function definition, right?
Right, yeah, I
You
don't
didn't write it as a
remember if I
function
did
definition.
that. I probably didn't do that and just had lambdas.
Yeah, okay. So now if we're writing it as a function definition, then it's slightly different. Then you only have 2 lambdas, right? Because now it's a function. So what you're saying is that you could have also defined it like this. So let's write it the way that you defined it. So sure, let's actually call it lambda f for the first argument, right? Lambda x, and then lambda y, and then what?
And then I'm pretty sure I just had in parentheses fxy.
Yep. So f is a function of 2 arguments. You feed it x and y, and then you close these 2 lambdas. Then you close that lambda, and then you close the define. And then if we were doing it like this instead, where instead of just defining curry as a name, we defined it as a function, then what would we have for the body?
I guess you just, instead of lambda f, you just have lambda x, lambda y, and then fxy still at
Yep.
the end.
So that's the implementation of curry. And this is the signature of the curry function, or the contract that it obeys. And then uncurry is similar, and flip are similar. It's really when you get to the point-free problems that it becomes slightly tricky. So I'll write the signatures of the other 2. And I did ask you to write signatures when on your submissions. So uncurry. Oh, and then there was also compose. So uncurried does the opposite thing. It takes a curried function. I'll write it like this. And then it returns a function of 2 arguments. And then compose, or my compose, so let's say the first argument is B to C. The second argument is A to B. And then from those 2 functions, it produces a function A to C. I'll write parentheses to make it easier. And then there was flip, but let's not worry about flip for the second. So let's think about the function that we had here. We had multiply. Elements, and then list. And then the definition of this function was that it mapped the following function: lambda x times x, or times elements. Actually, element is a bad name. Let's call it.
I think on the
N.
exam it was n.
Yep. So that's the lambda, and we're mapping this onto list. And then you didn't have to write a signature for these functions, but its signature was a number in a list of numbers to a list of numbers. And the idea was that we wanted to write it in something called point-free form. So we wanted to rewrite the definition as just being define, multiply, and then writing a definition that did not use lambdas. Instead, it used the 3 combinators that we had above. Well, 4 combinators, but you don't use flip for this problem. So the issue here is that, well, this define is already in some sense a lambda, and then there's a lambda inside the body. So if we're working this out, I don't have the answer written down, but I'm just going to show you how I think through it. And you only think through this after you've gotten to this. So I'm taking this approach because I'm used to these types of problems. I remember in first year undergrad, so this problem is usually set on Prabhakar's exams or on CS 145 exams on the midterm. And it's taken by first semester freshmen. And then this question is just unleashed on the midterm. And afterwards, all of the upper years sort of who take the class know this, that the question is there. And then they tell everyone, all of the really frustrated students about this problem, that point free should actually be called pointless. So it's a bit of a tradition. But let's see. So I don't think I solved the second part of this problem in first year on the paper exam. But later, now that I'm in graduate school, I was able to solve it in 5 minutes because of a bunch of skills that I had developed. So before I was really frustrated and wasn't able to solve it in time, and now it's not hard because you develop the skills. And again, that takes a lot of time. Right. So if we, for example, curry multiplication, then now this is a function that when taking a number produces a multiplication by that number function. Now let's look at map. map takes two arguments, and then the first argument should be this function applied to n. So in other words, and then the second argument that map takes is list. But that's good. So if we curry map, and then so let's see what happens when we curry map. So the type that this has in our context, so we're not going to use type variables. We're going to use very specific variables. The function that we're taking, this has type number to number. So map now takes number to number. And then it produces, so it takes the function of type number to number, and this is the curried version of map. Then it produces a function that takes a list of numbers to a list of numbers. Now, the first argument that we want to send to mult by is n, which is very convenient because that's the argument that we need to send into currying by multiplication. So we can produce a function number to number if we first take a number, then pass it to currying multiplication, and then pass that to the first argument of the curried version of map. Now we can't actually refer to that argument, so what we need to do is we need to compose both of these. So what if I write compose the curried version of map with the curried version of multiplication? Then what I get is a function. So the curried version of multiplication is, I should write the type of that this has. This is number to number to number. So in other words, if I take a number, I feed it into this, I get number to number, and then I take that and I feed it into curry. That's why I want to compose. So overall, that composition gives me number to list number to list number. But that function is a function of one argument. So it's already curried, but I want mult by to be a function of two arguments, so I have to uncurry this. And that's the answer to that problem. And sum of squares, this was worth 2 points because comparable to sum of squares, that function is much trickier. There, the problem is that you'd like to compose in both arguments. So you have to flip and then you have to unflip in order to make. So you want to compose in one argument, then you compose in one argument, then you flip it, then you compose in the other argument, then you flip it back because you need to have the original order, and then there's a curry and then there's an uncurry. But it's tricky. This is a tricky problem. And so only I think only two people or 3 people solved this version, 2 or 3 people got this. Anyway, but if you're not one of those people, you shouldn't be focusing on getting this problem. That was a tricky problem. You should be focusing on the first 2 problems, and then also the proof problems, which I haven't graded. I'll say something intelligent about the proof problems by email, and I'll also make a decision about what we're going to do for the final exam. because I don't want to lose people. And originally the final exam was going to be just logic. And in a sense, I want people to focus on logic, but I might add some of this earlier material to give people another chance at getting through it. Does that sound moderately reassuring?
Sure.
Anyone else? Thoughts? Or questions? So this was a postmortem in some detail. Okay, should we get back to logic? Okay, does anyone have any questions about logic that we've done so far? So last class we talked about and or nots. Sorry, and or. And now we're going to introduce negation and contradiction. So here is the last part of predicate proposition logic. This is contradiction in predicate logic. And nots in predicate logic. So before we discussed this idea that there, in the Boolean interpretation, we can talk about not A. And from a truth table perspective, the truth table for not A looked like this. Oh, and remember, we're not thinking about Boolean tables. Don't think about this. Truth tables. This is something that we're going to abandon, and we're going to explain in some way what the difference is. So if A is true, then not A is
false.
Yep, and then similarly false true. So really, that's the meaning of nots in classical logic. But we'll see that in intuitionistic logic, this is very different. I guess in classical logic, we can also talk about something called contradiction. Contradiction also has a truth table. So this symbol right here denotes contradiction. And can anyone guess what the truth table for contradiction is? It only has a single entry. False. So a truth table with n propositional variables has 2 to the n rows. So for example, the formula not A involves only a single propositional variable, and so there are 2 rows. Not has no propositional variables, so it has 1 row. 2 to the 0 is 1. In the language of propositional logic, from the Boolean valuation, their true and false can't appear in formulas. But you can talk about contradiction, which is sort of an encoding of false. And then you can talk about tautology, which is the opposite of contradiction, as not contradiction. And then that's just an encoding of true. So the purpose of contradiction as a language construct in classical logic is a way to encode true and false inside of formulas. But in the BHK interpretation, we have a very different version of it. So in the BHK interpretation, the BHK interpretation of, so before we said that's the BHK interpretation of a proof of A implies B is a construction that transforms a proof of A into a proof of B. And then we said the BHK interpretation of a proof of A and B was that it's a proof of A and a proof of B. And then for OR, similarly, a proof of A or B is a proof of A or a proof of B. So what should the BHK interpretation of a proof of contradiction be? What is a constructive way to prove something impossible, to prove something false?
To prove that the opposite is true?
Well, there is no opposites. It's just a proof of contradiction. So if the opposite of contradiction is tautology, then yes, tautology is true, but that doesn't mean that you've proven contradiction. To show that tautology is true doesn't mean that you've proven contradiction.
Right.
How do you do something impossible? Well, the answer is you don't. So the BHK interpretation of the proof of contradiction is that there is no such proof.
Would you have to prove that there's no proof?
No, the BHK interpretation is that there is no such proof. Or more succinctly, the BHK interpretation not of a proof of, but of the constructs is that it has no proof. So for all of the other ones we discussed, so this, and all of the other ones we discussed what the BHK interpretation of a proof of something is. This wording is sort of bad. Because already the better way to word it is not to talk about the BHK interpretation of a proof of contradiction, because from the outset, we've removed the a proof of clause here. Because the interpretation is at the outright that there can't be such a proof. So the more succinct interpretation is the better way to phrase it. The BHK interpretation of the language construct of contradiction is that it has no proof. So before we discussed, for example, implication. The BHK interpretation of implication was a function that does something to something. And that suggested what the proof term for implication should be. It should be a lambda. And similarly, the BHK interpretation of the proof of an AND statement suggested that the proof term should be a structure that stores two proofs. So what does this interpretation suggest that the proof term for contradiction is?
That there is no proof term?
Exactly. This suggests that there should be no proof term for contradiction. So in other words, in order to add the language construct of contradiction, we do not add any more proof terms. So the proof terms are as they were before. But for types, we add a new type. We add a new logical statement, and that's the statement of contradiction. And then this is just a constant. So for example, for the other types, there were arrow types, there were and types, and there were propositional variables. Contradiction has no internal structure. It's just the symbol of contradiction. Now, so in other words, there's no introduction rule for contradiction. So every single grammar construct has associated rules and an associated introduction and elimination rule. But, oh, no. Sorry, let me say that, so we don't give contradiction an introduction rule, but we should have a way to use contradiction, right? So if the introduction rule for contradiction is as strict as possible in that you can't prove it, how should you be able to use a contradiction?
We can try to eliminate it.
And what do you get when you eliminate it?
We get the opposite of them. Is that right? Wait,
That's
let me
one
think.
thing that you can get. So you can also get the statement that you individually are simultaneously the president and the pope. That's something that follows from contradiction as well. Think of contradiction as a magic wand. It's very difficult to acquire. In fact, it's impossible to acquire. But once you have your hands on contradiction, you're allowed to get anything. And this is called the principle of explosion. From contradiction, anything follows. And so, then what proof rule do we have? So we haven't added, so every single term variant in the language of terms has a proof rule associated with it. So for example, last time we had, for ands, we had one and introduction rule and two and elimination rules. And each one of those exactly corresponded to a proof rule. Although one of those proof rules had two versions, both a synthesis and a checking version, but we still sort of consider them the same rule. So because we've added one new construct, we should get one new proof rule. Although maybe it has both a type synthesis and checking version. Although the answer is no, it doesn't. It only has one version of one of those. So in a context gamma, let's give the proof rule. Suppose you have a term, and that term is a contradiction elimination applied to some term t. So the idea that from contradiction anything follows means that if you take any type whatsoever, let's say W, you can type check that term to that. This term type checks to any type. Now, what are the conditions for that term type checking to any type? So basically what I'm saying here is that the eliminator for contradiction is like waving your magic wand. So if you wave a magic wand, you get anything you want. Now let's say I wave something. What do I need to check in order to ensure that I get anything that I want?
That it is a magic wand that I'm
Yes.
wavering.
I'm actually waving a magic wand and not something random like a cat thinking that it's a magic wand. Then what do I want here?
T type checks to impossible.
Yes. So T type checks the contradiction. And so for synthesis, it should be impossible to synthesize a type because if you're eliminating contradiction, it should type check to anything. So if it type checks to anything at all, then it can type check to any other thing whatsoever. So synthesis is in general impossible, right? And for contradiction, this is the only proof rule that we add. So there is no introduction term. There is a single elimination term. The elimination term is as generous as possible. Now, if we have contradiction and there's no way to introduce it, why would this ever be something that comes up? How could this possibly be a useful thing to add to logic? Well, what's one logical statement that I could form using contradiction and then prove it?
Maybe that A or B implies A and B.
Well, that's something that you can prove using contradiction with using no other terms. But how would you actually write a theorem that has contradiction in it and prove it?
Maybe if your context already has a contradiction in it.
Yes, but let's suppose that I want to verify a sequent with an empty context. How would, in my calculation, I actually get contradiction in my context? You're on the right track. When do I add something to my context?
Implication introduction.
Yes, so I assume it, right? When I add it to my context.
Oh, so if a contradiction implies something?
Yes, so you can assume a contradiction. So you can have, for example, variables typing to contradiction in hypothetical reasoning via hypotheses, hypothetical reasoning. So to give an example, if we consider A implies A, what's the proof term for A implies A?
Lambda x dot x.
Yes. Now let's suppose that we actually consider any possible type whatsoever. So this doesn't just have to be a propositional variable. T is now a meta variable for any possible type. What's a proof term for that?
Wait, does the capital T match the other capital T?
Yes.
Then it's lambda x dot x.
Yes. So here, t is a metavariable for anything. E.g. t equals, let's say, A implies B implies C. If you have an arrow where the left-hand side is the same as the right-hand side, when I say a metavariable, I mean consistent substitution. The only time that you don't have consistent substitution is when you have things like grammar variants or non-terminals, and I've been very careful not to call them variables. Okay, now let's think about contradiction implies contradiction. So one proof term for contradiction implies contradiction is lambda x dot x. What is another proof term for contradiction implies contradiction? So in the empty context, give me another proof term.
I'm going to guess here. Lambda x dot contradiction elimination x.
Yes. Good. So instead of returning what you got is a magic wand. So you use your magic wand to make another magic wand. Right. So if you actually think about it in the way that I've been drawing stick figure pictures, this is you. This is a magic wand. There are two ways that you can get the magic wand. You can either like get the magic wand, or you can get the magic wand and then you can wave the magic wand and make another magic wand, and use the one that you made with your first magic wand. Okay, so this is a quick view about how contradiction works. Right, but why are we discussing contradiction? We wanted to discuss knots. So here's the thing. What is the BHK interpretation of a proof of knots T? So for a proof of A and B, we said it was a proof of A and a proof of B. We sort of looked at what we had, and if you think of each one of the constructions, so the language of terms itself has a grammar. So we had T, for example, and grammatically it was either a propositional variable or it was an arrow. Sorry, this is now as a grammar. Or it was an and, or it was an or. And then we also had not. And then if you looked at the BHK interpretation of the proofs of the first four, the first three variants after propositional variables, it was that a proof of an implication is a proof of the right-hand side, assuming the left-hand side. And then here it was a proof of the first thing and the second thing. So in a certain sense, the definition of what a proof of something was structurally recursive. It talked about it in terms of a proof of the a proof of the right-hand side, or it talked about it as a terms of a proof of the left-hand side and the right-hand side, right? So if we wanted to discuss this in a structurally recursive way, what would we be sort of led to say? That a proof of not T is what?
Well, it isn't a proof of T.
Right, but if we try and do it structurally recursively, we try and say something, and then we'd say something, 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 a proof of T, right? And that's a bit of an issue because we want to show that T doesn't have a proof. This should be that T should not have a proof. T should not have a proof. But how do we say that T doesn't have a proof? How do we show that it's impossible for T to have a proof?
That we can prove contradiction given T.
Exactly. So how do we say that proving T is impossible?
A proof of T implies contradiction.
Yep. So there is one thing that we know that is impossible. We know that proving contradiction is impossible. So if from T contradiction follows, then that shows that proving T is impossible. So definition, not T means T implies contradiction. So in fact, in the grammar that Proust uses, there is no AST node for nots. As soon as not gets parsed, it gets translated into whatever implies contradiction. So this is the definition of contradiction. Sorry, this is the definition of knots. Not means that whatever you're taking the knot of implies contradiction. So let's try and do, and of all of the previous concepts, this one might be trickier to get your head around because it involves negative thinking, but there's only a single proof rule. So that's a bit actually generous. That's on the lenient end, and it's a very easy proof rule to implement. So this is probably the easiest programming assignment, the third one. But then the proving assignments might be a bit trickier. So let's try this. Let's try a proof of, and then we're going to think about the rules that we had before. Contradiction or A implies A. How do I prove this? Oh, by the way, does anyone have any questions about that? Before we go on to proving this, does anyone have any questions about not and contradiction? So remember, there's only a single construct in the language of terms, and every single construct has proof rules corresponding to it. Well, one proof rule that might have a synthesis in a checking mode in the case of one of the rules for introduction has both a synthesis and a checking rule. All of the other ones only have a single one. But ignoring that fact, each grammar construct has a unique proof rule corresponding to it. That's why when we're checking proofs and running programs, they're structurally recursive on proof terms. So the fact that we've introduced a single construct in terms means that we should have a single proof rule. And then we introduce this one thing into the language of types, or the language of logical statements. And then the one proof rule for how do you use on contradiction elimination is that it type checks to anything. And then the premises is just that what you're using to get anything is indeed a magic wand, that T type checks to contradiction. And that's useful because we can form contradiction in hypothetical reasoning. We can have contradiction as a premises. And also, since it's impossible, it suggests what the VHK interpretation of not T should be. Not T means T implies contradiction. So a proof of not T is a proof of T implies contradiction. And contradiction is something that's impossible. But so here's a sort of trivial proposition that uses it. Contradiction or A implies A. But remember, we need to figure out, or this is a proposition that also uses the OR eliminator. So the OR eliminator was a bit tricky. I'll remind you of what that was as well. So in a context gamma, the OR eliminator is a three term structure. Let's say D, F, and G. So remember that if you have a T or W, then if it was T and W, we could get from that T, or we could get from that W. We could get each one from it. But from an OR statement, you aren't guaranteed to be able to get either one. So if you want to use it, you need to conclude some third type. And in order to conclude that third type, you needed ways to get from each one of the two things that you could have been given in an OR statement to the type that you want. And so does anyone remember what the premises of the OR elimination rule was? Anyone? So what about D? What has to happen to D? So let's say T or W. Did we do synthesis or checking here?
Synthesis.
Right. And then what about F?
F type checks to T implies V.
Good. And
G types checks to W implies
good.
V.
There we are. So this is the rule for, that is the rule associated to the term construct or elimination. So here we have an OR statement as a hypothesis. Anyway, how do we write this proof term? What's the first thing that we should do? It's an implication, right? What's one way to prove something implies something?
Wait, what is the associativity of this?
Implication has the lowest associativity. So the list of associativity, the precedence list, is that not has the highest precedence, then and or have equal precedence, and implication has the lowest precedence. So for example, if I wrote not A or B, that's not A, not consumes its argument first, and then or gets to go. And since implication is the lowest precedence, that means that or consumes its arguments first, and then implication consumes its arguments. What's immediately to the left of it and what's immediately to the right of it. But the first thing that happens is that not consumes what's immediately to the right of it. When you're actually writing this in Proust, you're going to probably have to fully parenthesize things, except for implications. We have a special rule for not fully parenthesizing implications. Okay, so what do we do? Good question.
Thanks. We start with the lambda x dot
Right?
or elimination of x.
Yep. So that's an or statement that we've been given.
I'm not sure what to do from here.
Okay. So what are the two? So now that we know the type, X has type T or W, right? Well, sorry, it has type contradiction or A, right? So what are the two other arguments that we have to pass into here? What would we like to conclude from it?
That contradiction implies A and that A implies A.
Oh, okay, those are the two factors. What we're trying to conclude from the or is A, right?
Yes.
So A takes the position of V, and then contradiction, or rather contradiction and A here take the place of T and W. So F should be contradiction implies A, and G should be what?
A implies A.
Yes. So how do I write the first one? Contradiction implies A.
Oh, another lambda.
Mm-hmm. What should we call the variable?
Y.
Sure. Then
Would it be
so
contradiction
Y.
elimination?
Oh, go ahead.
or,
Yes. On what?
A? I mean Y.
Yep. So Y, if you're given contradiction, then you use contradiction elimination on it, and then you get A. So that proves A there. And then the second term, A implies A, is what?
Lambda, you could call it Y, I guess, because it doesn't
Yep.
interfere with Y. Lambda Y dot Y.
Good. And so that term right there is a term of type contradiction, or A implies A. Any questions about that? Now let's consider the following. Let's consider A or not A. Sorry, A and not A. Implies B. So first off, how is this statement rewritten? Not, go ahead.
A and A implies contradiction, implies B.
And once again, the associativity of it is that and has higher precedence than implication. So it's implicitly parenthesized like this. Although when we wrote statements like A and B implies B and A, it was, I think, implicit to us and sort of suggested intuitively that the convention should be that and has a higher precedence than implication, right? So this is A and A implies contradiction. This all implies B. Right. So what we're actually proving is this. Not is just shorthand for A implies contradiction. Okay, well, how do we prove this? So first off, what would let us conclude B?
That A and A implies contradiction.
Yeah, but what rule do we use to conclude B?
Implication introduction.
Oh, implication in, right. Implication introduction means forming an abstraction. Yes, good. Thanks. Yeah. So the first thing that we do is we assume this, right? So now for X, we've gotten A and A implies contradiction. Now what do we do? What would let us conclude B?
Contradiction elimination.
Mm-hmm. How do I get contradiction?
Wait, why wouldn't it be and elimination?
And elimination gives you one of those two factors, right?
Right.
So and elimination could give you A implies contradiction, or it could give you A, right? But if you write that as the body of the lambda, then and you apply to X, then you're only going to get one of those two things. What the lambda returns should be something of type B. And the last thing that we do is we wave our magic wand. So that should be the outermost thing.
To get contradiction, we would use the second factor of the n, which is A implies contradiction. So we just need an A, which would be the first factor of the and
Right.
argument.
So in other words, the structure that I put inside of the and elimination at the top level is what?
Is and elimination 1 on X.
Oh, but when you say, well, that would give us A and contradiction, right?
It's
You're
the
saying
other
that
way
that's the
around.
top level most structure?
Yeah. The other way around. It should be elimination 0 on X.
Okay, but that gives us A. We still need contradiction. Neither of those give us contradiction. What actually
We
gets us
apply the
contradiction?
2, so it'll be
Right, so at the top level, then it's, go ahead.
What do you mean by on the top level?
Well, so let's look at the term that we're writing right now. At the top level, it's a lambda, right? If you
Yeah.
looked at it, for example, as an AST, let's look at the term we had before, right here. We could sort of write this as an AST. I'm going to choose to write X as a part of the node label. So maybe I could write it like this, lambda X. And then as its child, there's an OR elimination. Then it has 3 children. One is X. The other is lambda Y. Then not elimination. And then Y. And then this one is lambda Y, Y. So maybe that's one way that I could visualize this as an AST. But at the top level, this term is a lambda, right? So putting it another way, what's the last rule that we apply on the tree? The last rule that we apply, that's determined by the term, right? The algorithm is structurally recursive on terms. If I look at this term and I ask which variant is it in the grammar of terms, you'd say it's the lambda, right?
Yeah.
So that's what it says that, for example, the last rule that we use is implication introduction. Then what's the second last rule that we use? Well, it's the OR elimination rule. And then within that, there are 3 premises in that rule. And then in each of those premises, for example, for these ones, the rules that were used were implication introduction as their last ones. Then you used a variable rule. Whereas here you used contradiction elimination, and then you used the variable rule. Not including instances of the turn rule. The turn rule may have also been used. But ignoring those, that's the structure of the proof tree. So here, for example, this term at the top level is a lambda, right? Then at the next level, it's an OR elimination. And then inside there, what's inside there? What is the top level term? What kind of term is it?
Kind of term. I know it should be an elimination one on X, that which would
Oh, but when
give
you say, oh, okay, you say and elimination one on X.
That should be upside down, right? The and.
Oh, thank you. So that gives us what? That gives us A implies contradiction, right?
yeah, and we apply it on A.
Right, but we apply it. So at the top level, it's an application, right?
So I should say parentheses. Like,
Well,
or
no. You should have said at the top level, it's an application.
Okay, so I see.
Is it and elimination 0 on X?
Yes. So if I were going to draw, okay, so this is a proof term for A, and A implies contradiction, implies B. And if we look at this proof term as an AST, at the top level, it's an abstraction. Then it's an contradiction elimination. Then it's an application. Let's just write the word app manually. In Proust, there's a structure APP for applications. Then here, that structure is an and elimination one, and elimination 0, X, X. So that's the AST representation of this proof term. And that really tells us what the proof tree looks like as well, modulo instances of the turn rule. And then if you think about it in the way, you have a box that has a machine. Let's say you have, this is U. I did it in blue. And then you have a box that has two things inside it. One of them is, okay, a coin, and one of them is a vending machine for magic wands, right? So what do you do to do it? You go, right, let's put it in green. This is a coin. This is a vending machine for magic wands. You open the box, you take out the coin, you take out the vending machine, you put the coin in the vending machine, and then you wave it around, the wand that you get around. And that's processed exactly as represented by this proof term. But the application step was the putting the coin in the machine step. Does that make sense? Any questions?
Yeah, so we're doing lambda X on the very outside. And then we need a proof of A and something. Like it's an and statement. So why isn't it like and introduction or something like that?
Well, that's our hypothesis.
Oh, okay.
Is the ands.
Oh, so
that should answer your question, right? Okay, go ahead. Go ahead.
I think I get it now.
Mm. Right, so, right, we're assuming basically that we have a box with these two things in it. And then we're showing that under that hypothesis, you can get anything else. B is, let's say, a coffee, which I have here. Right. So that's how contradiction works. Proofs with contradiction might be slightly trickier to work around, but this is by far of the 3 implementation assignments the easiest one, because all that you have is a single rule, contradiction elimination. And that rule, that is a much simpler rule than the one for example, or elimination. Any more questions? Oh, and I'll have the assignment posted as soon as this lecture ends. I'll make it my priority to post the assignments. I'm going to post probably all 3 programming and all 3 proof assignments today. Actually, I see no reason why I wouldn't do that. Okay, let's take a break. Let's resume at 3:07. I'll keep these proof terms here for the moment. Okay, we're back. Does anyone have any questions? So I now want to discuss a bit about the difference between classical logic versus intuitionistic logic. So what we're doing is constructive. We are doing intuitionistic logic. So we are able to prove not statements. For example, if T implies contradiction, then if we can prove this, then we prove not T. This is just by definition. And in logic, this is called a refutation by contradiction. And this we're allowed to do. In our logic. It's just the very definition of not T is what says that we're allowed to do this. Now, there's also the idea that in classical logic, and it's not only in classical logic, and in most of mathematics, we like to prove things by contradiction. So I remember in undergrad, I took a commutative algebra class, and it was taught by a professor called Jason Bell. And he liked to keep some patterns going on in the class. In that class, we used an absurd amount of proofs by contradiction. Almost every single argument that we would wrote would begin with the words "suppose not." So he'd write down a proposition and he's like, how do we start the proof? What are the first two words that we say? And then everyone would just rhythmically chant, "suppose not." So what is proof by contradiction? A proof by contradiction is we assume not T. We assume that T and prove a contradiction. Hence T. If you think, for example, about Eudoxus's proof that two circles are to one another as the squares on their diameters, he supposed that the two circles were not to one another as the squares on their diameters. Then it was either bigger or it was smaller. And in each case, that led to contradiction. But what was his conclusion? His conclusion wasn't not the statement that he nodded, it was that two circles are to one another as the squares on their diameter. And that argument, really, what this uses is that if you, so not T implies contradiction. That was the hypothesis, that we assume not T and we get contradiction. That itself implies T. In other words,
Can we rewrite the not T as like T implies contradiction itself?
Let's do it the other way around. Let's rewrite the implies contradiction as a not. Then what do we get?
Not T?
Yes. Implies T. And this is called double negation elimination. And it is unprovable for us. It is unprovable in intuitionistic logic. So for example, if you showed that, and like as you said, if we fully expanded it, what would we get?
T implies contradiction, in parentheses, implies contradiction, close parentheses, implies T.
Yes. So what would a proof of this be, according to the BHK interpretation? It would have to be something that takes a proof of T implies contradiction, with parentheses going that way, and produce from that a proof of T. How do we actually constructively prove T from this? So now, I should also clarify that this is unprovable in general, for general T. You might take some very specific formula and substitute it for T, and for some specific formulas, it might work. But in general T, this is unprovable. And that's, and so the reason that this is unprovable is a bit less clear than the other big player in the game. Here is the statement that's classically okay. So here are, well, before I get to the big player, here are some other statements. There are things called De Morgan's laws. About how not behaves with and or statements. And so let's consider the statement, for example, not T or not W. Implies not T or W. Not T and W. So in general, when you negate an and statement, it becomes an or statement. Can we prove this? Like, let's try and construct a proof term for it. This one is provable, by the way. Okay, what do we do first?
Could we rewrite the thing first?
Yeah, a good point. T implies contradiction, or W implies contradiction. Implies, and then the way that brackets associate is that we can just write it like this, right?
Yes.
Okay, good. Rewriting it is the correct first step. You should always rewrite it first. Good. Now what do we do?
Abstraction. Lambda
Yes.
x.
So now x is going to have the first factor. And then what?
Another one, another
Yeah.
lambda.
So right now, if you were doing this in Proust, you would have a context in which this is x and this is y. Now we'd like to get contradiction from that. So x is an or statement. What do we do?
Or elimination, perhaps.
Now what's the first? Okay, what's the first factor?
X.
T implies contradiction.
X. Right. Now, okay, right. Now, what are the type? What's the type of the first thing that we want here? You were saying?
We can use either one. T implies contradiction or W implies contradiction because we also have a proof of T and a proof of W, right?
Yes.
From what?
No, but for the or statement only has one of these. The or statement is either T implies contradiction or W implies contradiction. You don't know which. In the first branch, you're handling the case where you were given the first one, right?
I see. Okay. Yes.
So let's call this, this is the meta variable, this goes for the meta variable f, and this what goes for the meta variable g. Okay, so the f actually stands for what term? So f, we want to produce some term of type T implies contradiction, and we're working in a context where we have a proof of T and W. So what do we do?
And elimination?
We are trying to prove this, right?
Using abstraction again.
Right. So what do you want to call the variable? Let's just call it A. Z,
A,
sure.
okay.
Now you're trying to prove contradiction in a context where you have, well, X, Y, and this assumption Z. So this assumption right here is bound to Z. Well, what would let us get contradiction?
Another abstraction, right?
An abstraction will always do an arrow type. We want to produce contradiction as the type.
Contradiction. We need T implies. Oh, we can either use T or W or T implies contradiction.
Right. T implies contradiction is bound to Z. But at the top level, what do we have?
Application.
Good. So what's the first factor of the application? What's the function? What are we using?
Z.
Yeah. And then that takes something of type T. How do we get something of type T?
And elimination.
Good. oops, I wrote an or again. 0 or 1
0
on.
Y.
on Y. Yeah.
So this gives us something of type T. Z is T implies contradiction. We use that, we get contradiction, and that's what we were supposed to get when we assumed Z. Now what about the second factor? Let's also call this lambda Z. Now what? So now Z is going to be W implies contradiction.
It's basically the
Is
same thing, except it's and elimination 1.
Yep. So that closes the Z and that closes the and elimination. So that is the proof term. This is the proof term for, well, we can write it in either not form or this form, but it's more instructive to write it like this. So this version of De Morgan's law we were able to prove. Now, the other version going in the backwards direction, is it just going in the backwards direction? Yep. Going in the backwards direction, on the other hand, so not T and W implies not T or not W is not provable. In intuitionistic logic. So I've just told you essentially on authority that first, the statement of double negation elimination, or let's call the statement alpha, double negation elimination. Then let's call this statement beta, this version of De Morgan's laws. But the final version, and this is the one that's most apparent to the intuition why it isn't provable, and that is the law of excluded middle. And this law doesn't, well, I guess it is the statement that T or not T. And in classical logic, if we consider Boolean tables, so if we have T here, and then we have not T here, and then we have T or not T, we can fill out what the table is. Or rather, I drew these in blue. So we did this Boolean table before, and again, I'm de-emphasizing the Boolean evaluation. And I suppose it's slightly annoying that we called it C. But okay, the green T and F are true and false. So if T is true or if T is false, then what is not T, respectively?
False and true.
Yes, and then true or false is
True and true.
and then true. So in the Boolean valuation, this is true. But in intuitionistic logic, here is why it's intuitively obvious that this statement has no proof. A proof, or rather for all T. For some T, it might happen. But for example, if we consider A or not A, so here T is a meta variable for any formula. For certain formulas, that's clear. So for example, if we consider A or sorry, A implies A or not A implies A, that statement is certainly provable. That statement has the following proof rule. You do a or intro 0, and then you supply lambda xx, right? That is the proof of A implies A or not A implies A. A implies A is true. And so we've proven A implies A.
But the problem is A itself does not have a proof in an empty context, right?
Yes. So in this one, A doesn't have a proof, but similarly, not A doesn't have a proof either. How do you just prove that A implies contradiction? Why should A imply contradiction, right? If you think about it, what this says is that for any logical formula, you can either prove T or you can prove not T. And what would a proof of that be? A proof of that would have to be a proof of T or a proof of not T. So in other words, a proof of the law of excluded middle would have to be some language construct that no matter for what logical formula was either able to prove the first factor or the second factor. And that would also suggest that that formula would be able to tell which one of the two was true. And that seems very overpowered. That seems to say that there should be some algorithm for deciding truth, and that that algorithm should be encodable in a proof term. But that's apart from the fact that it's not true that every single term or its negation has a proof. A doesn't have a proof. Not A doesn't have a proof either. So in this case, this statement, A or not A, is actually not provable. Whereas on the other hand, this statement is provable. Whereas in classical logic, for the Boolean valuation says that the statement is always true. And in fact, so let's call the statement gamma. And finally, I want to give one more statement. And this is called Peirce's law. And the reason that Peirce's law is noteworthy is that it's a statement that involves only implication. It doesn't involve any ands, ors, nots. It just involves implication. And that statement is T implies W. Well, I guess I don't need to bracket it. T implies W implies T. Implies T. No, sorry, I do need to bracket it. It's T implies W implies T implies T. So this statement is not provable either. And this statement was explicitly constructed to be in the implication fragments. So this is a statement in the implication fragment. I mean, if T and W are formulas in the implication fragment, then it's a statement in the implication fragment. Again, for every single one of these formulas, if T and W are metavariables and you replace them with certain formulas, they might be provable. But if you consider, for example, A implies B implies A implies A, then this is going to be not provable. So this is not generally provable, and this specific instance where you just use propositional variables is definitely not provable. And this is in the implication fragments. So the reason that I wrote the rules not just with propositional variables, but with metavariables ranging over any proposition is that none of these are provable, but we could take any of them to be a law that holds in general. So one is Peirce's law, one is the law of excluded middle, one is this version of De Morgan's law, and then the other one is double negation elimination. And it turns out that if any one of these is an axiom, then you can prove all of the rest. The rest follow. In fact, your logic becomes what is called complete with respect to the Boolean interpretation. And what this means is that any true formable is provable. Any true formula is provable. So I've introduced this word completeness. And intuitionistic logic just lacks this one thing, but if you insert it, suddenly you're able to prove any true statements. Now, all of our proof terms had some computational interpretation in a certain sense. Taking one of these as an axiom breaks that illusion. There's no computational interpretation for a proof of the law of excluded middle in general. It would have to be the meaning of the computational term would have to be some process which decided which one of the two factors is true and produced a proof for it. And that really breaks our analogy that we're programming in logic. And that doesn't seem to be a problem right now, but we're about to go into predicate logic. And in predicate logic, that would be sort of disastrous to everything that we're doing, because we actually want to perform computation on proof terms. And so that's actually the difference between intuitionistic logic and classical logic. If you added to the logic that we have so far any one of these four rules, then every single true statement in the Boolean notion of truth, which isn't the only notion of truth, would be provable. So this is a non-examinable part of this class. This is just a digression about me telling you some things which are generally important in understanding logic, but don't correspond to anything that will be tested directly in the course. Any thoughts?
Is there like an official, like which one of these four we take as an axiom?
There isn't. Although typically one does law of excluded middle.
All right.
So the two obvious choices are either law of excluded middle or double negation elimination. Peirce's law is like one of the ones that you wouldn't take as an axiom. It was constructed explicitly in order to make something that could be stated with only implications, but it isn't very usable.
Yeah, I can see that.
And then ditto, this specific De Morgan's law is somewhat random, but law of excluded middle would probably be your best option. Now, there's actually a very remarkable theorem. This is a magical result. However, it's fine. To work in intuitionistic logic. So if a formula can be proven with any of those things, then we're working in classical logic. So that proof system in other words, intuitionistic propositional logic plus any of alpha, beta, gamma, or delta is called classical logic. Classical propositional logic. I'll call it CPL. But we don't lose anything in intuitionistic logic. And because of the following hard results. So this is hard to prove. If T is classically provable, which is the same as saying it's true, is true in the Boolean by completeness of classical logic, then not T is intuitionistically provable. The proof of this result is non-constructive. So the proof of this theorem, which is outside of the logical systems in which we're currently working, gives a non-constructive demonstration that if T is classically provable, in other words, if it's true, then in fact there exists an intuitionistic proof, a proof in the logical system that we've developed so far for not T. And then in classical logic, you can always prove, you always have double negation elimination. So if you want to prove things intuitionistically, just take your result, put two negations in front of them, and then if you can prove it classically, you can prove it intuitionistically. Now, this is a remarkable result. So this result somewhat reassures us that it's fine to work intuitionistically. We're not actually losing anything in this system of logic. And then Prabhakar's notes have a link where you can read more about that results. I'd also like to bring up a very cool section in his notes, which I might discuss on the last lecture, and that's a section on what are called Kripke semantics, which is a different notion of truth. It's a notion of truth in which the law of excluded middle is false, in which all of the four results above, alpha through delta, can be proven false. Rather not proven false, but false by the Kripke model. And then he also demonstrates that intuitionistic logic is complete with respect to the Kripke interpretation, and also that it's sound. So the other property apart from completeness is soundness. So this is like, by the way, a proof system is sound with respect to a notion of truth. If every provable formula is true. So soundness should be a bare minimum property of proof systems. You don't want to have a proof system in which you can prove a contradiction. So for example, in a sense, if you looked at the proof system of ancient Greek philosophy before Parmenides, Parmenides showed that it was not sound. He found a contradiction in Greek philosophy. And that resulted in everything being burnt to the ground and then started up in a much more careful way. So in general, when we write logic, soundness is a very important property. Soundness is what tells us at the bare minimum that what we're doing makes sense. If it's not sound, then everything can be destroyed by simply pointing out a way to, for example, if the system has contradiction, to prove contradiction. Or prove any false formula. Contradiction is just a very nice way to encode falseness.
For a definition,
And then completeness.
should it be like if and only
Go ahead.
if? Should it be an
Sorry,
if?
say it again.
So for a definition of soundness, should the if be an if and only if?
No, completeness is the opposite direction. So a proof system is complete. I should write that. I wrote complete above, but I'll write it here. A proof system is complete with respect to a notion of truth. If what? If every, say it. Well, what's the reverse direction of soundness? Soundness said that every provable formula is true. Completeness says what?
Doesn't the completeness of a system mean like it can handle any question considering that you can throw at it?
Well, considering that it can what?
Handle any question that you throw at it that relates to the system.
I mean, you can give it a false formula and it can't prove a false formula, right?
Yeah, so that wouldn't be complete then?
No. You should, you'd really hope that every single false formula is not provable, right? We don't want to prove false formulas. What we want to prove is what?
If every true formula is provable?
Yes. So we definitely don't, soundness says that you can't prove false formulas. Completeness says that true formulas are provable. So if we use non-classical logic informally, soundness says that false formulas are unprovable. Completeness says that true formulas are provable. And both soundness and completeness are ideas that relate a proof system to a notion of truth. So they make sense only when you've specified both the proof system and the notion of truth. And we certainly know that there are many proof systems because, for example, in this class, we started in logic with just the implicational fragment. That was one proof system. And then we added more things to it, and that became a different and bigger proof system. Now, we only gave one notion of truth. We only gave the Boolean notion of truth. But maybe in the last lecture, I'm not sure I'll have time for it, I probably won't, but you should read Prabhakar's notes. He gives another notion of truth called the Kripke model. And he shows that intuitionistic logic is both sound and complete with respect to the Kripke notion of truth. Neither soundness nor completeness implies each other, so neither is an if and only if statement. Okay, but so right now, me talking about soundness and completeness, that's a digression. This isn't part of the examinable material in the course. So this unit on classical versus intuitionistic, this is not examinable. Let's move on to our next unit. So I'm going to do a tiny bit of predicate logic today. And I'll underline this because this is really the last quarter of the class. This is a big unit. So at the beginning of the class, we had statements. What did we have informally? We had nats. And we had, for example, lists. And we were able to make statements like, so what was the first problem that you proved on the homework? It was commutativity of addition. What was the statement of the commutative property of addition?
For all nats n and m.
Yes.
Wait, is this like PF1 basically?
Yep.
Okay, for all nats n and m, then parentheses plus nm equals parentheses plus mn.
Yep. And if we think about how plus was defined, it was in some sense a structural recursive definition on nats, right? We defined what plus was by considering what plus should be on the second factor for z and of s of z. So what we had is, so we considered things like this, and then this relied on structurally recursive. Definition of plus. Which roughly was that plus nz was, I'm going to write it as equal, n, and that plus n s of k was what?
Plus snk. Wait, plus s of n.
No.
K.
No, that was add. Plus is structurally recursive.
Oh yeah, sorry. S of plus nk.
Good. So, okay, here are like the various things that come in. First off, there's equality. Next off, there's quantified statements. Next off, there's actual natural numbers. And natural numbers come with a recursion principle. So we want logic to be able to handle something like the natural numbers, and that should come with a recursive principle. Then we're talking about equality. And at the beginning of the course in the first week, I really should have scared you about what equality is. Equality is something complicated. And then we have for all statements. So all of these three things, these are features that we'd like to add to our logic. So just to keep track of a list, we have quantifiers. We have equality. And then we have nats which are an inductive structure. And associated induction and recursion principles. And we'd like to extend our logic to be able to handle all of these. So this is a logic wish list. If we're able to add all of these to our logic, and NATs now have an inductive principle, then what's preventing us from actually being able to write down a proof of this proposition, including a definition of plus? And that definition of plus will include in it a notion that plus makes sense within our logical system. So that's our goal. We'd like to add all of this to logic so we can prove statements like this. And you can also add lists, and then you can even prove statements about lists. So in fact, if you on your own extend it for lists, then you can prove any proposition that you proved on the midterms or the homeworks in Proust. So that's on a very top level. That's what we want. Our goal is to prove, it's to be very ambitious and to be able to prove everything that we proved informally in the logical system. But all of these things need to be added. Any questions?
So a quantifier is a for all, right?
So they're actually, yeah, good. There are two different quantifiers. There are for all, and we're also going to talk about exists. So I can give you examples of those. So let's talk a bit about number theory. So now we're actually talking about natural numbers and integers. So for numbers, we say, so by numbers, okay, let's say for integers. And by integers, I mean ellipsis, -2, -1, 0, 1, 2, ellipsis. We say, let's say m divides n. What does it mean that one number divides another number?
That you can fit an integer number of n inside m.
Right. Now, what does it mean fit an integer number of?
That there exists a number such that if you multiply it by,
Yes.
I don't know if it's, I actually don't know the order. So if you multiply by n, it gives m. Is that the order?
Okay, we can choose either one because multiplication is commutative. So you can give the definition either way because for numbers, it doesn't matter. For things that aren't commutative, I guess you'd have to choose one. And you probably, if you used it in a paper where you were talking about divisibility in systems that are not commutative, then you'd have to clarify which one you meant. But for now, let's just give the definition. If there exists k so that km equals n. So perhaps by divides, I mean evenly divides. To say that a number evenly divides another number means that some multiple of the first is the same as the second. But here, there's this notion of there exists. Right? So for example, prove for me that 3 divides 6. How do you do this?
Let k equal 2.
Yes, consider k equals 2, then what?
K, well, 3 times 2 is 6, and therefore 3 times k is 6.
Yes. So that's proof of an exist statement. So remember, for proving a for all statement, we had the anonymous method, right? So proving a for all statement was done by the anonymous method. Proving an exist statement involves providing a specific, what I call witness. It's a witness to the truth of the statement. For exist statement says that there's some witness that witnesses truth. A for all statement says that any element that you choose you have to get a true proposition. Whereas to prove an exist statement, you don't prove it for everyone. You show that there's a number that exists that satisfies the statements. So that suggests how we prove. This suggests what the proof rule is for exist statements. And for exist statements, the actual name is existential. Statements. And then, by the way, for all statements are called universal statements. So those are two fancy, pretentious names that you can use for quantified statements. Universal and existential. But let's get to existential statements at the end of the class. For now, let's think about universal statements. And the reason that we're doing this is because all of the informal propositions that we've considered have been universal statements. So actually, there are two programming assignments for this section of the class. But the second one is going to be sort of a last priority thing. There's an assignment that handles existentials, but really the important assignment is the assignment that handles universals. Because after you handle universals, you'll be able to prove those, the statements that we considered before. And you know what's really cool? It's that none of these statements actually involve any of the logical connectives apart from implication. There are no ands, ors, and nots. So we're going to have implications. That's sort of, we always have implications. That's perhaps the most basic logical construct, implications. And then we're going to add to it all of these three things: equalities, quantifiers, and inductive structures like NATs. And also bool. But mainly NAT. So just with NAT's equality, quantifiers, and implication, we'll be able to prove a statement like this. And that'll be a really good place to get to at the end of the class. Because we started, the perspective that you're supposed to have is we're working in a system. Systems are governed by rules. I can follow rules. Now, the rules are really rigid, but really, there's a lot that I can do within the confines of the rules, and that's where creativity comes in. You understand what the rules of the game that you're playing are, but then the actual plays that you make, that's abstract, and you have to think abstractly outside of the system and figure out how the system works, and cracking each system, figuring out what its machinations are, and producing new systems. These are really good ways to practice just abstract reasoning skills in their most general form. So that's why this is a really good set of material, I think, for an introductory mathematics class, apart from the fact that it also teaches you about logic and basic mathematics that is used later. It's that, but at the same time, it thinks about itself, and it thinks about itself in ways that train abstract reasoning skills. So that's why I wanted to teach this material as it stands, with a combination of both first the informal and programming material, and then the logic material. Putting them together into a single course, I think hopefully really worked. But again, that's if I have people following me, which I'm going to need to fight for in the last week. I should also mention that when I was proposing this course, I mean, I wrote many pages just as an organ. So this is something like that was done in February or March. Well, okay, this was done last year. Here are some notes, rather, that I have on this material with the implicational section. And then for the actual course proposal, I wrote two double-sided pages. And in the very last week, I got to the predicate logic sections. And I wrote, the students will definitely understand the meaning of the for all and exist symbols prior to formal logic, prior to the formal logic part of this course. That was point 1. Point 2, as for the formal part, quoting Wittgenstein following the conclusion of his thesis defense to Russell and Moore, don't worry, I know you'll never understand it. And then I crossed out never and wrote presently not. So this is the section that I anticipated to be very tricky. And I'm going to actually have to put in a lot of work on this weekend because handling it is going to be super delicate. This is the most technically complicated part of the class, and it's very subtle. But at first, you're going to have to sort of accept what we've presented, and then it'll take a while to understand it. So it's hard to unpack. But once you've unpacked it and thought through everything, then you will have, from the ground up, built a system of reasoning. You will have understand every single piece that goes into reasoning about proving a statement like the commutativity of addition. So is the goal clear?
So the goal, at least a nearby goal at the moment, is to cover Liechtenstein's thesis?
Oh, no. Well, after Wittgenstein did his thesis defenses, the Tractatus. Well, so the Tractatus actually introduced logical tables. I actually have a copy here in this collection of Wittgenstein. For example, if you look at logical tables there, so Wittgenstein was definitely a hard proponent of the Boolean interpretation. Where are logical tables? Here. So one of these is the law of excluded middle.
Okay.
And then there are other things. But no, anyway, after defending the Tractatus, which again isn't just about logic, it's about mysticism and a bunch of other things, but they're cool. Russell and Moore were sitting there, and then he tapped them on the shoulder and said, "Don't worry, I know you'll never understand," which he said to the people on his thesis committee, which is a very bold thing to do. But you are allowed to do it when you're Wittgenstein. Okay, the line was that I didn't expect people to understand the predicate logic portion of this class in February. I currently think differently. I currently have a clear presentation of this material, although it's very, very delicate. But the goal is to have a logic which is able to handle all of the informal proofs that you did. So I won't, I'll have this perhaps as a bonus assignment. And actually, because strings of equality are somewhat painful to work with, and you might almost want to introduce new things to Proust if you want to do that. But the statement that's actually reasonable to do in the version that we're going to do is the plus z statement. So what was the statement of plus z? For all nats n, what?
Plus z with n equals n.
Yes. So this statement, its proof does not involve as large a nested string of equalities as this one. Nested equalities are going to be sort of painful because transitivity of equality is going to be an explicit proof rule. And it's going to have a lot of annotations in it, and writing all of them explicitly is going to be painful. Equality is going to be the hardest part about this. But this statement isn't that bad. For this statement, on the other hand, the easiest way to prove it would be to add a few lines into Proust that let you write proof terms, that let you generate proof terms. And you sort of generate the proof term for this as opposed to writing it yourself manually. But it's doable if you do that. So this one requires a bit of mechanization, automate the production of the proof term from the string of equalities. But this one, my hope is that everyone will go through it and do this. And the nice thing is that when we start Proust with predicate logic, we start from the ground up with the implication fragments and then add universal quantification. So if you're not caught up on implementing all of the previous logical quantifiers, you start from square one on predicate logic. So this weekend, I would like people to get through as many of the other assignments as possible, but at a certain point next week, you should switch over to prioritizing predicate logic. Now that programming assignment is a bit harder, and I'm going to consider offering people the chance to give up on the programming assignment and for me to give them a complete implementation so that they can just work on the proof. Because I really, really, really like for everyone in this class to write a proof of this formally. That's sort of a very good way to bookend the course. We started by proving this as one of our first statements in the commutativity, but this is the one that I would hope that everyone would write a proof for. And then implementing lists and proving properties about lists is a challenge for which I won't have test cases, but if you do it, send me an email and I'll be happy. Okay, any more questions? Okay, let's get on with it. So the interesting thing to note about statements like this is that, for example, 3 is a number, or let's say Z is a nat. But Z equals Z is a logical statement, is a proposition. Or let's just say a logical statement. Now, the things that we had were that logical statements were types. And then right now, it's not clear what Z is proving. Is Z a proof? Well, not should be a type. And to say that Z is a not should be saying that Z is a term of type not. So for example, if we were writing typing statements, it should be true that Z has type not. So that suggests some very weird things going on. If we think of terms as being proofs and types as being propositions, then we have something like Z is a proof of the theorem not. So that's odd. That's an interesting way to think about it. If we think of types as logical statements and terms as proof terms, then we think of like a number as being a proof of the theorem numbers. And the other thing that's weird that's going on is that proof terms appears in a type. Which is Z equals Z. So for example, what would be a good name for the logical statement that something equals itself? Does anyone know? So that's called reflexivity. Says, let's say, x equals x. And reflexivity is going to be a proof term. This will be a proof construct. So for example, we're going to have things like reflexivity applied to Z as being a proof of the proposition Z equals Z. So the thing on the right-hand side is a term. But on the left-hand side, we have a type. But that type inside of it has terms. So types and terms are now going to be mixed. There is a mixing. Of types and terms. And these are two things that are very weird to deal with at first. We kept types and terms very separate in our treatment of propositional logic. Types were just these capital letters and then arrows formed from those capital letters. And then terms were all a bunch of other things. Terms could be variables. We usually wrote them with lowercase letters. Here we have, and then it was sort of clear that what logical formula a type meant. A was a logical atom, but afterwards when you said A implies A, well, whatever A is, A implies A. A implies B implies A. But here, you suddenly have terms like Z and types like not. And not doesn't really look like a logical statement. It looks more like a set. So this not is a type. and Z is a term. So that's the first weirdness. And the second weirdness is that now types themselves have terms involved in them if we want to talk about equality of two terms. And these are things that just sort of come up when you want to talk about these things in a type or in a term context. And it's really weird at first. These two notions are going to be really hard to get over. It's not clear yet why they're hard to get over, but as we're going through it, it'll lead to a lot of confusion. So this is me warning you as to what the most difficult conceptual parts are when dealing with predicate logic. Any questions? So this is called the weirdness. And there are two sources of it. That's one, and that's the other. So what we actually have in here is universal quantification. And this is where higher order logic comes in. You are not allowed to do this in first order logic for reasons that we'll see. Specifically, you're able to do something in universal quantification in higher order logic that's typically would not be allowed in a math class. And it's a really strong benefit of working with higher order logic. So where do I want to start? Let's see. Right. So first off, I want to say, what are we quantifying over? We want to say for all terms of a given type. So to our language of types. Okay, I'll write down what our language of types is right now. We're going to start from the ground up, starting from the implication fragments. Well, actually, let's say it like this. One kind of type, universal types, have the form, and then we'd be tempted to write for all, and then you write what your variable is. So you can say, for example, X. I'll use a capital X. Inside some type. So in other words, for all terms of a given type, we have some logical statements. Now, because this dot is not allowed in Proust, because it's used in Racket, we actually write the following. We replace the dot with an arrow, but it's going to be a single arrow. And we'll see why that is. So what we're allowed to say is if T is any type, then I conform statements saying that for all terms x of that type, that is certain that actually I should write this as though it were not a grammar, as though it were so okay, that's logical formula W holds. Now, if we think about it, for example, you can say that, so let's suppose that natural numbers make sense. We might want to say something like, for all natural numbers n, that n equals n. So I haven't made sense of natural numbers yet, but these are the type of sentences that we'd like to have. And then what is W in this case? So in this case, X is little n, T is not, and W is n equals n. But notice that W involves n. In general, W may involve, and by the way, X is necessarily a variable. W may involve X. So in other words, the type might have a variable in it, and the meaning of that variable will be in that it is bound to the quantifier. So what should the BHK interpretation of then the BHK interpretation of a proof of for all X of type T that W holds is what? Any guesses? Is anyone following? I want to get people back on track.
Read the example. Like, how would I read that out loud?
For all natural numbers n, or for all nats n, n equals n. You wouldn't read the arrow. The arrow is just a delimiter that we replaced instead of a dot. So you'd say for all nats n, n equals n. That's actually a good point. I should write that down here. Read as for all nats n, n equals n.
So couldn't W be said to be a function of X, which is supplied by xt?
W might make reference to X, and X is only a variable. X is only meaningful because of the quantifier. So they're called quantifiers because they quantify the variable over the domain of quantification,
Yes.
which is in this case the type.
Mhm. And so that would mean that W is also defined over that particular type, right?
W may or may not make reference to X. So for example, you can also say that for all natural numbers, N, that then we can give some statement like, let's say Z equals Z. So that statement is true, but it doesn't make reference to N, right?
Yeah.
This statement is entirely independent of the quantifier. So you're also allowed to make statements like this. You're allowed to. Sometimes it's helpful, sometimes it's not, but you're allowed to do that. But more importantly, you're also allowed to do it when N is made reference to inside of the type.
Yeah.
So how we proved things with the anonymous method. And I suggested that the anonymous method had a computational interpretation. So when we talk about the BHK interpretation of a proof of a universal statement, that will have to do with the computational interpretation of the anonymous method. So the idea behind the anonymous method was that we wanted to prove something was true for all nats. So we let N stand for any nat, and if N stood for any nat under no other assumptions, just a label, we were able to prove the statement. Then by substituting for N any nat, we'd get like a valid proof. So there came this computational interpretation of substitution, which is also the computational interpretation for functions, isn't it? And in the new version of the notes, I said that for hypothetical reasoning, which is implication, that the computational interpretation of hypothetical reasoning was similar to the computational interpretation of a universal statement. So if we think about it, for example, to use, let's say, the statement that plus Zn equals N implies plus Z S of N equals S of N, what did we need to do? Well, we technically used it in a proof by structural induction. But if we wanted to use it as a hypothetical reasoning, we would need to prove the left-hand side. And conclude the right-hand side. Right? So technically, this was probably a bad example because this actual implication got used by a different proof rule. It got used by the proof rule for structural induction, not for the elimination of hypothetical reasoning. But now to use the statements that, let's say for all N in nat, N equals N, how would you use it? what can we conclude from that statement? What follows from this statement?
That if you let n be any net, then n equals n.
Right. In particular, for example, what's an example of a NAT?
S of z.
Yes, we can specialize to use a proof of the statements. We can specialize to any NATs, e.g. S of z, to get S of z equals S of z. So we use a for all statement by specializing it. And that causes substitution in the proof term. And then we use a hypothetical reasoning statement by, I'll do a better example. That was a bad example. To use, let's say, a proof of T implies W, you fill in the uses of T with a proof of T. To get a proof of W. So proofs of implications, in order to use them, you need to supply a proof of the left-hand side. Whereas a proof of a for all statement, you use it by supplying any term in the domain of quantification, right? So what's then the BHK interpretation of a proof of this? So remember, the BHK interpretation of a proof of T implies W is a construction that transforms a proof of T into a proof of W.
So we need a construction that takes something of type T and produces a proof of W.
Good. So let me write that down. Is a construction that takes a term of type T. Let's call that term actually, let's say it in terms of proofs. Let's say that takes a proof. Or that takes actually, let me 1 second quickly check something. What I want to say it's in the right way. I think this was the one place where it was said in 2 different ways in Prabhalkar's notes, and I wanted to choose the better one of the 2. Okay, you know what? He writes it in terms of objects X of type T. That sort of chimes with intuition better because we think of NATs as being proofs of NATs. That's a bit odd. Let's say, yeah, fine, takes an object / term of, let's call it X, little x. Okay, let's call it little t of type t, and produces what? What did you say it produces?
A proof of W.
Right. So now let's look at it. Let's look at this. Does anyone have any comments about this?
Why did we choose the term construction instead of function or something like
Okay, last time we used the word function. Whoops. Because I'd like to think about it as a generalized function. Actually, in Prabalker's notes, he uses construction in both instances. Actually, you know what? I'm fine using function as well. Good. Good. Function.
But this function isn't a lambda, right?
Oh, but it will be actually a lambda.
Okay.
That was what comes next. Okay, but sure. That comes next, but it's a function that takes an object, a term t of type t, and produces a proof of W. Okay, let's think about this. Let's look at the statement below. So what would a proof of this be? It would be some construction that takes, so what is W? What is the metavariable W replaced with in this case?
n equals n.
Right. So the original statement is for all knots n equals n, right? Now consider the statement n equals n on its own. That doesn't make sense. What does n mean? On its own, W is n equals n. What is n? Right? So for example, here, we said that the term specialized to, we can specialize to S of Z to get a proof of S of Z equals S of Z, right? So going back to this, what are we actually producing a proof of? So here W would be n equals n. But what we'd actually like to say is something like this, where n gets what?
Substituted with something of type nat.
Yes, and the specific thing is in our BHK interpretation statements. I gave the term a name t.
Oh, little t? Yeah.
Yep. I'll write that in blue. And okay, the way that I write that is, so the variable here was x. So I'll take x and then I'll write a maps to symbol, and then I'll put the term little t. So this is the BHK interpretation of a proof of a universal statement. It's a function that takes a term t of type t and produces a proof of W, but where x, the variable of quantification, has been replaced with the provided term.
So that funky arrow is basically substitution?
Yes. Well, before we used it for evaluates to, but when we write it in square brackets like this, this means substitution.
Okay.
means substitutes t for x. I'm actually not sure what grammatically, does anyone know what the better way to say it means? Substitutes.
Substitute t for x.
Yes, t for x. Yeah, that's the right way to say it. In W. Now, okay, so you already said it before. This suggests that the proof term for a universal statement should be is what? Or rather should be.
A function.
Yeah, but our proof terms are, functions are actually,
Lambdas.
yeah. Or I'm going to write it as an abstraction. Now I'm also going to write, however, the resulting type depends on the value of the parameter given. So if you give it z, you get a proof of z equals z. If you give it s of z, you get a proof of s of z equals s of z. And in general, such functions are said to have what are called dependent types. In the world of programming languages, it's a function whose such that the type of its output depends on the value of its arguments. And this is very hard to implement in programming languages. Some programming languages like Haskell are doing it soon, but even then they can't do a full implementation of it. But for proof assistance, it's exactly what we need, because we need dependent types to make logical statements like for all nats n, and then some logical statement that depends on n. So dependent types is right what we need in order to do this. And then instead of just being a function, it'll be a function, but we are going to interpret its output as being of type W after we make a substitution, if x appears in the function. Now, what if x does not appear in the what if x does not appear in W? Then a proof of for all, let's say, x in t, W is what? Is a function that takes what? So, okay, when I say what, let's say that, let's now say it's a term of type t is, we're going to call a proof of t. Takes, let's say, a proof of t and produces a proof of W, but since, right, so just W, since, so we haven't defined what substitution is yet, but it should be desirable that however we define substitution, if X doesn't appear in W, then substitution should do nothing to W, right? So in other words, if X does not appear in W, a universal type is the same as an arrow type. So this is just implication. In other words, implication is a special case of for all. In which X does not appear in W.
If X doesn't appear in W, then why do we still need a proof of T?
Well, because let's think about it. For all terms X of type A, we have A. X doesn't appear in W here, right?
Correct.
But what would a proof term for it be? If implication is a special case.
A function that takes a proof of A and outputs a proof of A, which is lambda x dot x.
Yeah, or let's also do lambda a dot a. Just so capital X and little x don't get confused. Right. So here we don't have to do substitution. No matter what you give it, it returns something of type A. Whereas if X appeared in A, it would return something of type A after substitution for the value of the parameter. So in fact, we don't need implication anymore. We're not going to have arrow types. Arrow types are just going to be a special notation of for all. And the way that we do this, if we don't care about X, we write for all, and then instead of writing X, we write underscore in T, W. So underscore means don't care. And so let's say T implies W, is now shorthand for all underscore in T, W. So now Proust will actually take implications and it'll transform them into universal statements like this. In the same way that not T is shorthand for T implies contradiction. That not T was shorthand for T implies contradiction. I say was because we now no longer have not or contradiction. We haven't added them back in yet. Right now, we're just going to talk about universal statements, and that already includes arrows. But if we add not back in, which isn't going to be on one of the assignments, but you can do on your own, then in fact, now it's going to stand for all underscore in T contradiction. Okay, so that looks like that's enough for today. I'm going to post all of the homeworks and I'm going to send you an email with details about how to do the homework. And then for everyone who submitted work on the midterm, thank you for doing that. And I'm happy that you put in the work to do it. So grades are going to be fine. Don't worry about that. Okay, any questions?
So you said how many homework will due Friday?
Well, I'm going to put at most one programming assignment due on Friday. I'm probably going to put them due one each day for several days in a row.
Okay.
Maybe I'll make two of the assignments, the implementing contradiction and proving things by contradiction, due on the same day because the implementation for contradiction is shorter, and because by that time you will have already implemented two sets of things, and you'll find the implementation of contradiction to be almost tedious because it's the same thing as you were doing before, exactly the same thing. The first programming assignment is going to be the hardest. After that, they're all just the same thing. I assure you that it's going to get tedious at a certain point.
Okay, got it.
The first one will be frustrating, but the other ones will be tedious. And then the proofs are just writing proof terms. So without using Proust at all, we wrote some proof terms. But Proust will allow you to do it in, Proust will allow you to do it in an interactive way. So here was, for example, a proof term that we wrote for De Morgan's laws. For Proust, you could put question marks in it, and it'll fill in holes and allow you to fill in those holes piece by piece. And again, the best resource for reading about this is Prabhakar's notes. You should read his notes. Lucky.
Which sections in particular would be the most useful?
Right, good. So the statement, I think we should be all familiar with the section 2.4 by now, which introduces proof terms for implications. But if, so you should start potentially at section 2.3, which just introduces the proof system without proof terms. I can write down annotations for this. I mean, basically 2.3 onwards until the last section, but I can actually write down what those sections are. And this is a good review of what we've done. So section 2.2 about the Boolean interpretation is going to be useless for the homework. Is on the Boolean interpretation. And this is useless for homework. Okay, and now here are the lines about conceptually important things. So 2.3 is the proof system for implication. 2.4 is about proof terms. So this is where we change sequence to be having proof terms. 2.5 is an beginning Proust implementation. And you shouldn't necessarily go through all the details of the implementation. Then section 2.6 is about holes and getting assistance with proofs. So it's not important that you read this. So both of these are okay, actually, wait. For programming, so this is not significant, not super important. But this section is very important. Because it talks about, explains the match statements. It explains the match. And then there's the link to match. See also documents on pattern matching. Then section 2.7 is about the other logical connectives. So that has all of the proof rules that we care about. And this is also important, but it's basically what I did in the last two classes. Basically, there were last two classes. And propositional logic starts in the next chapter, but you don't have to worry about that for now. And then section 2.8 is about classical versus intuitionistic, which is what I discussed today, which is also not super important. I'll write those two sections for completeness. Again, not important for homework, and then 2.9 is Kripke models. Spelling gets. Oh, okay. Which is like extra contents. And then this is not homework related. But so 2.5 and 2.7 are the most important sections for this homework.
Thank you.
And the notes are really well written. And I'll get to posting the assignment as soon as possible. Any other questions? Okay, have a nice day. I'll see you on Monday.
See you.
Bye.
Bye.